对了，4月份还没有做好。是啊，但他本来是英。
Hello, hello. Echo. And then video. Right, working. Share the screen. Yeah, I think we still have to copy in the slides. Okay.
Chen, where's the USB?
Yeah, pressure. So are you available right now? Let me check.
Yeah, I think I'm a co-host right now.
Continue. Right, and then you just have to share. Okay, let's just check whether the audio is.
Yeah, it should work.
Okay.
Volume down a little bit.
Yeah.
It's a little bit too loud. Every time it happens.
How about this? Do you want to play?
I'll try it. I'm trying to try it one more time. Make it 50 or something. Make it full screen. This is the first slide.
Yeah,
It's the first slide, right? Okay, cool. Can do the intro. Okay, sure. All right, thank you everyone for coming. I know it's a bad weather outside there, so really appreciate your attendance. Today it's really our honor to have our first industry talk this semester, as we have been organizing ICON seminar for the whole semester. This is our first one industry for this semester, and we'll have Mr. Walter Kosiak, Dr. Chen Wang, and Tento Sugiato, who come from Aptiv. And Mr. Walter Kosiak is right now an engineering manager at Aptiv. He has worked at Aptiv for the duration of his career in the fields of integrated circuit design, passive safety, active safety, driver assistance, and automated vehicles. His area of expertise include a lot of things, including ADAS, advanced driving, advanced driver assistance systems, automated driving, and threat assessment and warning algorithms. A lot of different things. I won't go into all those details. And Mr. Kosiak is an inventor of 24 US patents and was a member of the team that completed the first US coast-to-coast automated drive in 2015. And along with Mr. Kosiak, we have also Dr. Chen Wang, who is a feature development engineer at Aptiv, where he is currently working on motion planning for automated valet parking. And Dr. Wang received his PhD degree from Ohio State University, and he has published more than 20 papers and held more than 10 patents. Also have Mr. Tento Sugiato, who is a software engineer at Aptiv, where he right now is focused on developing motion planning algorithms for autonomous parking, which they will share a lot of details, interesting details during the seminar. And Mr. Sugiato holds a master's degree in mechanical engineering from Ohio State University. Okay, without further ado, let's welcome the speakers.
Thank you, everyone. I appreciate you inviting us here on such a beautiful day outside. And I commend you for braving the weather to be here today. So thank you very much. I hope you find this this interesting. And these guys are the best, right? And I brought them here because I expect some hard questions. So they're all going to go to those guys. So thank you. We've got just a kind of a splash screen here. Is a little bit of an intro to Aptiv. So safe, green, and connected. That's really what we're all about. This is kind of a snapshot of the company. Again, we've used this safe, green, and connected mission probably for the past 5 or 6 years. It's really been unchanged. It's kind of the founding values that we're going after right now. We want to eliminate accidents, increase mobility, make the world a greener and more sustainable place. We have 160,000 employees in 46 different countries, manufacturing facilities across the world, 12 major tech centers. We're from the Indiana Tech Center, which is in Carmel, which is on the north side of Indianapolis. We also have a facility in Westfield. It's a heavy duty lab and I guess a validation facility. And we also have our vehicle garages and our technicians there. And then we have 18,000 engineers, right? So I think that resonates well with this group of people. We do some hiring, right, every year, both interns and obviously full-time. And I'll go into some of those details at the end of the talk, so that if you are interested in a career at Aptiv, we can talk about that. This is kind of a snapshot really of where our tech centers and our manufacturing sites are. And we kind of break our systems into what we call the brain and the nervous system, right? The brain is where all the compute is. The nervous system is the interconnections, the data, the sensing for that. So when we talk about safe, and I'm not going to focus on all three of these pillars, but just the one on the left. When we talk about safe, we're talking about 0 fatalities, right? That's our goal. Save lives, reduce injuries and damage. The bullets along the side there, perception systems, sensor fusion, software, right? The software platform needs to be scalable. Of course, we have a large part of our business is just in wiring and interconnects, right? It's kind of a cash cow for us. We're really, I guess, best in class in the industry there. So we pride ourselves on that product line. What's new in the cars now is, voice rec, gesture rec, as well as driver monitoring. And then, of course, when we get into automated driving, right, you can't disregard functional safety, right? These L3, L4 systems, they have a lot of ASIL-D components on them. So let's get into our platform. I'm not sure how many of you are focused really on the software side of things or the mechanical side of things, right? But an automated system has to have, a combination of both the hardware and the software. So we'll talk quite a bit about our hardware platform, but also a little bit about our software platform as well. One thing I did want to point out on this slide is, Aptiv was the first tier 1 to put a radar on the road with the 1999 Jaguar for adaptive cruise control. So how many of you guys have driven cars with adaptive cruise control, or what about lane centering? Okay, we got a few here. Blind spot warning. Okay, and have any of you had your automated emergency braking system activate on you? Wow. Now, did it activate when it should have? That's the real question. There's a big balance in, maximizing performance and, prediction time for a crash, right? Versus, false alarms. You don't want your car to brake for nothing, right? Or maybe for a pop can or for a shadow on the road that happens to look like a pedestrian, right? And cause an accident behind you. So there's really a lot of validation that goes into these systems. A key focus for us is scalability, okay? Not only on the hardware side of things, but also on the software side. See, not all of you have, level 2+ or level 3 vehicles, right, that you drive. The vast majority of the vehicles that come out of these plants and are on the roads today are basic commuter cars, right? They have certain safety systems that they have to have, they're mandated, or the new car assessment programs require them, just for, I guess, competitiveness, right? To sell a car, you have to have so many stars of safety rating, right, these days. So those are on every baseline car, but only a few percent of these vehicles that come out in the US today have like level 2+ systems, right? So going down the same factory line, right, there's 80% that have just your basic minimum system. There's 10% that's mid, and then maybe there's 2 or 3% that are the real high end. So how do you make that so that it's affordable, right, for the OEM, right, to sell these things and also to be able to manufacture them? So we spend a lot of time on that. These are the basic components that can comprise an advanced safety or an ADAS, an automated driving vehicle. There's the brain right there. Generally, there's a forward-looking camera, At a minimum, you need that for traffic signs, for lane marker detection. Most of the time, it's used in sensor fusion systems for detecting and classifying pedestrians versus vehicles versus poles. Thank you. You'll see these green markers are what we call convenience systems, right? How many of you have like auto park assist, where you hit the button and your car will park itself? Yeah, I mean, not a lot of people use that, right? But in other countries, especially actually in China, right, that's a big deal, right? Because their parking spaces are very tight, right? And people don't know how to park a car anymore, right? You ask my kids, right? It takes them, they'll give up and they'll go, they'll park a couple blocks away so that they can have a pull-through parking lot, right? Or parking spot. So, but we have bird's eye view cameras and up to 12 ultrasonics on the vehicle to help with this automated parking feature. Generally, the L2 systems will have 4 corner radars that allow detection of blind spot warnings. It'll detect cars in the adjacent lane, and they also help with their overlapping beams with coverage for crossing pedestrians and things like that. Of course, your long range radar, which is generally what's used for adaptive cruise control on the highway, where you have to detect vehicles at 250 or 200 or 250 meters away, etc. So this is what comprises the overall system. When we put a system into production, right, it has the feature content, which is, what you touch and feel in the car, right? How well does it maintain the lane center going around a curve, right? How well will it actually detect a fast approaching vehicle from the rear, right? Where you have to see that a long way. Maybe that's in a curve behind you too. And you don't want your blind spot warning to be going off. For instance, if that car is actually in your lane and not in the adjacent lane, or maybe 2 lanes over, right? So that those algorithms really are what these guys do, right? That's my group and what these guys do, right? Sensor fusion, that's on the perception side. It's very critical because if you bring garbage into their algorithms are going to produce garbage, right? Systems integration, this is how to make it cost effective, how to make it plug together, make sure that we have all the functional safety aspects covered, and all of the other quality systems. Validation testing, a lot of it's done with software in the loop, hardware in the loop, simulation work, right? This digital twin concept. However, there's no replacing so many miles on the road, right? On public roads, right? These guys do driving. We have fleets of drivers that do driving, right? All of us, right, get what we call tier 2 automated driver training every year at a test track, right? Where we get to have the most fun all year, right? You've been in a car out of control, hitting cones, squealing tires, right? But it's all in the aspect of making sure, that we're safe out there, right? Because we're building these engineering development vehicles, right? There's prototype hardware, prototype software. There's not all the built-in functional safety and diagnostics, right? So we don't want to harm ourselves or anyone else that's out there. So, if something goes wrong, right, and the car starts going sideways, right, we need to know how to react for that. So. Scalability. This is where I thought it's hard to tell where one slide ends and the other one begins, right? There's only supposed to be 3 cars in the slide. So if you look at the basic L0 system, right, that's what it consists of, right? It has a minimum set of components to do the basic ADAS functions, right? Plus whatever convenience functions like, backup cameras and, the beep, beep, beep warning systems on the back of your car. The mid-level system, right now we add more capability, more sensors. There's, your NCAP star ratings will go up, and you'll have more convenience features like blind spot warning with the rear corner radars, etc. And eventually, when you get to L2 plus, that's all in, right? The stuff we do really isn't for robo-taxis, right? The stuff we work on is for personally owned vehicles, right? It may be with everybody from Tesla to General Motors, right? Or NIO or somebody like that. Could be Rivian and NIO like startups, or it could be more traditional, Stellantis, Ford, GM folks. But it's basically, high volume passenger vehicles around the world. So. Okay. One of the focuses that we have is we exploit our radars maybe more than other of our competitors, right? There's folks out there like Mobileye, Tesla even, that are trying to get radars off the vehicle. We think they're important. We think they can sense things, right? And do things that cameras can't. Of course, cameras can do things that radars can't, right? So the power is really infusing them together, right? But we are attempting to, improve and prioritize, right, and exploit, right, the capabilities of radars, right, today, including, doing some stuff with machine learning that none of our competitors are working on. One thing that it does is, there's a lot of concerns about data privacy, right? So if you're recording a lot of video, right, there's faces on there, there's license plates on there, all that stuff has to be blurred, right, before it's stored, right? And, there's always going to be concerns about data privacy with cameras. There's not yet with radars, right? Nobody can actually determine who you are, right, or which vehicle is which with a radar yet. So, maybe with imaging radars that day will come, right? But right now that's not the case. And really, a radar is lower cost than a camera, right? A camera plus the CV vision, right, that goes with the camera. I brought a few samples here. You guys are welcome to come up after the pitch. There's a couple of radars. We sell these radars for $20 to $25, right, in volume, right? Hard to believe all the technology in here. That's what it has. Some cameras and our standard type of our brain radar central controller. So. Again, when we talk about different modalities of perception, right, they're all good at certain things. The power really comes into, how to exploit the combination of them, right? How to allow, redundancy and functionality, how to optimize the limitations of one sensor with the strengths of another, yet not get confounded when, two are voting and one says yes and the other says no, who do you believe, right? LiDARs are just barely scratching the surface when it comes to high volume automotive production, right? There are, some companies out there, Innoviz amongst others, right, that believe they have a product that's marketable, right? And, those may be coming into high volume production here in the next few years. But for now, it's radars and cameras, right, that are dominating this space. Of course, there's ultrasonics for parking. But they're $2 per sensor, right? And they're only very short range, so they can be used for parking and low speed maneuvering, but certainly not high speeds it's required for normal public road driving. So in terms of architecture, right? We talk about scalability. And cost, right? Cost is a big driver in the automotive industry, right? The reason those are $20 to $25 a piece is because they're commodities, right? If we have 10 million vehicles out there with our sensors on them, and let's say 5 million of them have 4 radars, right? I mean, that's a lot of sensors, right? So the automakers don't have a lot of profit margin, right? And they squeeze it out of the suppliers as well, right? So it's a pretty competitive market that we're in. So what we try to do is enhance our profitability by coming up with smarter solutions, right? One of these is, we've reached a tipping point in ADAS and automated driving systems, right? Where instead of it being, the baseline vehicle having basically no functionality and only the high-end vehicles having a little functionality. When you have that type of a system, it makes sense to have standalone controllers, right, for each application. Your blind spot warning radar will have, all the smarts in it to do, the warning and alert functions, right? Now that we have blind spot warning as baseline, we have automated braking as baseline. So what we want to do is we want to take the smarts out of the individual components that are mounted, outside on the periphery of the vehicle where they have to do the sensing. Right, we'll bring the smarts in here, and then we'll allow the outside just to be, basically dumb sensors, right? I mean, the world is analog, right? And what we want to do is digitize it right away, right? And then send that information to the super brain, right? And then let them process it. So our systems over the last couple of years have gone from kind of a discrete standalone systems that are kind of plugged together, right, with a low bandwidth interface, right, to these I guess, digital sensors, right, that are on the outside skin of the vehicle with a high bandwidth interconnect to the super brain that does the processing. And that really, what that also allows is for the software to be scalable too, right? So now all of a sudden, you can plug and play extra sensors, right, on this bus topology, right? And you can also plug and play software modules into your stack, right, to do the end-to-end features. One of the things I wanted to talk about here is sensor fusion and this idea of, one sensor isn't good enough, right? If you look at this picture here, what it's supposed to depict is, the truck, the heavy duty truck that's right in front of the host vehicle, right? It can be seen by the radar and the camera, right? The forward-looking camera and all the radars can see that truck. So you see multiple boxes around that. However, when you get to the vehicles on the left and the bicycle on the right, it's only part of those are seen, right? Because now you're occluded, right? Because of that truck that's directly in front of your sensors that are like in the middle of the vehicle, right? You can't see around the edges of that truck to see the stuff that's in the adjacent lanes, just ahead of the back of that truck. So the thing you get with the corner radars in this case, right, is because of their perspective, right, they're already outboard, so they can see along the edge, right? So the other thing that's cool about radars is it can actually bounce under a vehicle and see the vehicle in front of it, right? So when we took these standalone controllers that were the sensor and the smarts, when we took the smarts out of it, it made the box smaller, more easy to package, right? The packaging constraints on a production vehicle are very tight, right? I mean, you wouldn't think it, right? But every cubic centimeter of that car is spoken for, right? So you have to fight against someone else to make space for your stuff, right? And that's never easy, right? Similarly, a great thing about radars, just another plug, is it's buried beneath the fascia, right? So from a styling aspect, right, the styling office at these OEMs, right, they love radars because they can do whatever they want over the radar, right, with plastic, not with metal, right? It doesn't affect their styling. So again, we had a 70% reduction in size once we pulled that out of there. Similar with cameras, the camera here is this little guy, right? And that's an example of the one I have over there. The other thing about cameras, right? These imagers are CMOS, right? And CMOS doesn't work at high temps, right? So your passenger compartment, I mean, believe it or not, with sun loading, right? It gets really hot, right? It's really hot. Now you add on top of that the fact that you've got an 8 megapixel camera and a high-end SoC in there crunching numbers, right? And the die temp and the box temp inside that unit gets huge, right? And all of a sudden the camera starts shutting down. Well, not shutting down, but performance goes down, right? And yet you still have to work at those temps, you know, that a normal passenger compartment can see sun loading, right? So, you know, we're limited on how many watts, right, we can put into our package, right, in that location in the headliner. So by getting the smarts out of there, right, and putting it somewhere that's cooler and in the shade, right, you know, we can do more stuff. We can have, you know, bigger imagers up there. Okay, and then like I say, the central controller, you know, really what limits these central controllers anymore? I mean, cost is a factor, right? But you know, there's Moore's law, right? These things, they get more powerful all the time, right? The cost keeps coming down, right? So you need to exploit that, right? Sensing costs don't go down nearly as fast as, you know, chip costs, right? So the more we can put into that central controller, the better off we are. The other thing is with all these standalone controllers, right, you have to run their applications all the time, right? So when you add up the number of, you know, MIPS or you know, the processing resources and memory, right, that's required individually, right, it's always going to be less than one single controller that, you know, I don't have to worry about doing parking when I'm, you know, out on the highway doing high speed, you know, highway pilot, right, type of functions and vice versa. So this type of scalability is really important. Mass, harness size, you know, how much power, you know, all of these again are improvements that we see with our satellite architecture. So we have our next gen architecture really that we're putting together now is it breaks the problem into 3 tiers, right? We have core functionality, plus functionality, and pro functionality. And I'll cover more of these details going forward, but you know, it steps up in improved sensing and perception capability, as well as I guess autonomy levels, and then also you know, NCAP safety ratings. So these are the functionalities that we get with Core, Plus, and Pro. And again, you know, Core represents, you know, L0 to L1, Plus is up to L2, and then Pro would be L2 plus, right? So you might ask, well, you know, why doesn't this include L3, maybe L4 parking? Because the slide's a little bit old. Our company, you know, we had several L3 programs when COVID hit, right? Those were canceled by the customer. And then after COVID, the customers have been very slow to come back with L3, right? Because they just aren't certain how well the public is going to receive them, right? So now we're starting to see like Mercedes, right, out there with an L3 traffic jam pilot, right? That's becoming well received. So we're getting more and more inquiries, right, for L3. Now L3 is always going to start with you know, L3 is basically the driver's mind off the problem, right? His eyes and his mind can be elsewhere, you know, fiddling with the phone, whatever, right? Reading the paper, right? Today's systems for up to L2 plus, they require the driver to be engaged. His hands and feet may not be on the controls, right? But his eyes and mind are supposed to be engaged, right? So there's fail safes like driver cameras that are in there, you know, the twitch the steering wheel every now and then to fake it that your hands are on it, things like that, right? So it's coming, but you know, like a lot of technologies, the technology is there, you know, before it's either cost effective, right, or the public perception is ready for it yet. So. Okay, so machine learning, especially for radars, right? These are some corner cases, right, for you know, automated driving that, you know, cameras have a hard time with by themselves, right? The picture on the left is, you know, an obstacle on the road, in this case, a tire, right? It's important to understand whether an object is over drivable or not, right? So let's say it's an L3 system, you're not paying attention, and you hit that tire with your automated vehicle because he didn't think it was a threat, right? That car is likely to go out of control. Okay, I mean, depending on where you hit it, right? It's likely to go out of control though. I mean, we need to be able to detect that, you know, and either avoid or automatically or warn the driver in time that they can, you know, take over and avoid that. You know, this bicyclist in amongst a whole bunch of clutter, right, and other moving objects, right? That's hard to detect. You know, in this case, it's in the rain. It looks like it's out there today, but you know, that's a hard one to detect, right? So we're similarly, you know, urban pedestrian environment, and then, you know, in a tunnel for lighting, you know, there's not necessarily marks on the wall, right, that a camera can understand that that's, you know, essentially a tunnel or a you know, the road edge in this case, right? So, you know, we're using supervised learning, right, machine learning and neural networks, right, with our radars to help solve these problems in a radar-centric fashion, so that when we couple that those radar outputs, right, with the camera, you know, they have their own neural networks and machine learning, right, that it does a better job of really understanding the environment around us. We're also trying to make more use and smarter use of driver cameras, right? In this case, what this picture is supposed to depict is, you know, there's a person crossing the street. However, the driver's gaze, right, is he's looking at these objects over here, right, in the opposite direction where this person is going, right? The light may change, right, and he may start pulling ahead without knowing that this guy, you know, was in the, you know, maybe the blind spot of his A-pillar, right, as they're starting to cross right in front of the corner of the bumper. So the idea is that, you know, you give smart alerts to the driver, right? If the driver's looking in the direction of the threat, right, he decides to go anyway, right? Well, I mean, that's a little different than if he's looking completely opposite direction and he decides to go. So there's nothing that irks, you know, customers more than warning them when it's not really a warning, right? Maybe that's some of you guys too. Aptiv's #1 in interior driver camera monitoring, by the way. So not all of our customers buy all the software from Aptiv, right? This is more on software scalability than hardware now, right? We have a lot of customers that buy all of our feature functions, you know, essentially end to end, right? All the perception software, right? The assessment, localization, behavior, planning, control, right? We provide it all, right? As one full stack. But we have a lot of customers that, you know, they like to do certain things themselves, right? Customers really like to own the feature function algorithms, okay? Because that's where they connect with their customer. You know, how does the car feel when it slows down in traffic, right? Will it bias over for large trucks, or, you know, will it move over in construction zones? You know, this is how they connect with their customer, right? This is where their customers touch and feel the product, right? So they like to have ownership of that, right? So a lot of the, especially, you know, maybe the safety leaders, you would think, right? A lot of the luxury brands, you know, they will invest, right, in the feature function software development themselves. So we basically have to have other modules, right, that will plug into them, right? They may, you know, in this case, here's a forward-looking radar for BMW, comes from a different company, right? We supply the camera and the corner radars, right? But they, you know, they integrate those themselves, right? So in this automotive industry, right? I mean, I guess to survive, you have to be flexible, right? I think we talked, this satellite architecture is really what allows us to be successful and to provide value to our customers, right? We're not, Aptiv isn't just a build to print company, right? All of these guys have a whole bunch of patents, right? We come up with innovations, and that allows us to provide value to the customer that they can't just get from anybody else off the street. So, I mean, it's what makes our job fun too. I'd like to switch topics now and talk about road safety. Who knows what VRUs stands for? Excellent. Okay. So take some time to take in these charts right here. What they compare is for pedestrians, cyclists, and motorcyclists, right? The overall number of fatalities for the last 10, 11 years. And they compare it with Japan, Europe, and the US, right? The thing you're going to see is, pedestrians, we've had a 70% increase in pedestrian deaths in the last 10 years, right? Japan and Europe have declined, right? Cyclists, we may be on parity depending on how you curve fit, right? I'm sorry. Europe and Japan are either, the same or slightly decreasing. We've gone up almost 60% in cyclist fatalities, right? Similarly with motorcyclists, we've gone up, Europe and Japan have gone down, right? That's not a good sign, right? Not a good sign. So I guess the bottom line is, we look at traffic statistics like this, and, we try to understand where the biggest problems are, right? And then we try to solve them, right? I mean, I got into this career, because, I wanted to save lives, right? It's kind of a holier than thou mission, right? At least when you have a bad day at work and you go home, you could say, well, at least I was trying to save lives today, right? But so, when we see things like this, it bothers us, right? So the scenarios on the right here basically talk about the ones that are the worst for pedestrians and cyclists, right? And I'll go into some animations here a little bit later, but I think the takeaway here is, though, that most of the problems with pedestrians come at night or under low light conditions, right? So what does that tell you? It tells you the camera is not seeing far enough, right? Not seeing far enough. The other thing that happens quite a bit is what we call straight crossing scenarios, right? Where they're outside the field of view of the camera, right? And by the time the camera detects them as they're coming in close to the car, right? I mean, the closer you are to the car, the narrower that coverage, right? So I mean, in many cases, your standard ADAS camera can't see the corners of the front corners of your bumper, right? It's inside that. Cyclists, again, low light. Motorcycles, interestingly, less happen at night. Most of them happen with this left turn across path, right? So left turn across path is a situation where you have an oncoming vehicle and the host vehicle doesn't see him and just turns and hits him, right? So that's left turn across path. So, when you look at these problems, what are ways to solve this, right? So again, AEB systems are the things that will help save lives with cyclists and pedestrians. For motorcycles, we really need AEB systems with wider field of view coverage as well. So this plot here is an interesting plot. It's not just for VRUs, but it's all crash types, right? Mapped into, I guess what you could say is the type of accident, the way NHTSA codes their accidents. It's either at intersections, road departures, rear ending, right, and so on and so forth, control loss, etc. So and what's shown around the outside, or what they believe is the best mitigation system to solve those problems, right? Certainly, road departures, lane departure warning, road lane keeping, lane centering, road departure warning. These are the things, right, that are gonna help with that. Those are kind of some simple ones, right? V to X, right? It's perceived that will help at intersections. The problem is the infrastructure cost, right? For that, a DSRC or 5G radio on your car isn't that expensive, but if you have to have, a signalized intersection, right, controller that's sending that information, right? And then a map of the intersection, right? So you understand the lanes and stuff like that. So, it's not an easy problem. We still have, 35 to 40,000 deaths, right, in the U.S. Due to traffic fatalities. Here's some animations. It shows some of the testing we do. What you'll see, this should replay, auto replay. Okay. What you're going to see is the target coming in on the left. As it comes in, you're going to see a progression of alerts and mitigation that comes up here. This is a forward collision warning, a tone or a light. This is brake support. So, it's what we call a brake assist, where, many cases a driver will touch the brake pedal, but they don't actually stop the car, right? They don't decelerate as much as the car will allow you to decelerate to avoid a wreck. So we enable this brake support. So if we sense the driver is depressing the brake pedal, but they're not doing it hard enough, then we'll kick in, a little extra decel. And then there's a pre-brake, which is a low-level brake, and then AEB, which is just full braking, right? So, the target, maybe we'll see it a little better here. We used to use interns from Purdue, but they got a little expensive. So now we go to this foam target, and it's on this little motorized skateboard. Okay, and the skateboard is GPS controlled, so it can have whatever trajectory longitudinal, lateral that you want it to have. So here's a right turn right in front of that cyclist. We do these tests not only for development, but they're also certification tests, right? For the either US Euro NCAP, China NCAP, right? Whatever certifications done. When a customer puts a car on the marketplace, right, we have to have a certification test done. Here's the next one. Again, a cyclist. We overtake a cyclist and then kind of cut them off, right? So you'll see him kind of lag behind us, and then we cut him off right away. Some of these tests aren't yet certifiable, right? This one is a European test that basically comes out in 2025, but we're already doing development and testing for that. Here's another one on the other side, right? We pass up that target. You can see it here. And then as we slow down to make that right turn, he catches up with us. He doesn't slow down, right? Maybe he doesn't see that we have a turn signal on or something like that. And he keeps going, thinking, he has the right of way, right? So we turn and we have to stop here, right, before we get them. And then here's a motorcycle left turn across pass. Of course, that's not a motorcycle, right? But it's a surrogate vehicle, but it's the same kind of thing, right? For whatever reason, people have a hard time seeing motorcycles as they're turning, right? So if you're a cyclist, be aware of that, motorcyclist. Okay, so at this time, I'd like to turn the stage over to Chien. He's going to talk a little bit about our highly automated parking applications.
Hi everyone. So my name is Qian Wang.
I joined Aptiv in 2018 and has been working for Walt in the parking team for almost 4.5 years, like another PhD program. So
But you're paid more.
so both Temple and me and I are working on the motion planning for automated parking. So I think we can start from a video, which is just 2 months ago in the CES 2023 in Vegas, and this short video is showing our how our automated parking system works. So briefly, the user communicate to the car, send a command via phone app, like a valet park, and then the car will drive itself to a designated parking area. And during parking, the car can do the collision avoidance by the motion planning's cruise planner, and stopping for a crossing pedestrian or moving around the stationary obstacle. Once the car is in the parking area, and then the parking space banding and parking space selection module will work to select the best available parking spot. And then finally the motion planner slot planner will maneuver the car into the selected parking spot. And then once the user wants to summon the car, and he will again send a communication message through a phone app like a valet pickup. So the car will drive itself to the driver or user to finalize the pickup. And during the automated valet parking development, we do face some challenges. The first one is the prediction of the trajectory of moving road users. The road users could be pedestrian, like cyclists and even cars. But here today I only focus on the pedestrians' trajectory prediction. So this is a typical parking laws in the United States. And for predicting the trajectory of the moving pedestrians, we typically use several methods, like motion models, like constant velocity or constant turning rate and acceleration, or a combination of them. And then, but this method typically only work for 1 second, maybe 2 or 3 seconds for a car, but for pedestrians, only about 1 second. For longer duration prediction, so we need to use like event-based machine learning training. For example, we know where the pedestrian is heading to, like there's a building and there's a shopping mall entrance. So we know pedestrian will move to there. So machine learning can help us to know what's the stage is in the trajectory. And also some researchers developed some like social LSTM, mainly working on the like a human-human interaction. For example, there are a lot of pedestrians, and then uses social LSTM can provide something like constraints to what the pedestrian will move. But I would say like even we have this method to predict trajectory of a moving pedestrian or a pedestrian in a parking lot is pretty challenging. For example, if our driverless car detect pedestrians moving, for example, the pedestrian line is moving to the right side with a speed 0.5 meters per second, it doesn't mean the pedestrian will, in the next few seconds, it will maintain the speed and maintain the moving orientation. It may end up, he may end up stop at the trunk of the car to open the trunk and optimize something. And for example, a pedestrian 2, when we detect that he stands still. So it's very difficult to predict which direction he will move to. For example, if this is a small parking plaza and there are multiple like shopping stores around this plaza, so you don't know if it's a random parking lot. We have never trained. We have trained that we don't know where the pedestrian is heading to. And some researchers claim that can use the heading orientation or heading rotation, head rotation, or even the gaze angle to estimate the motion direction. But I would say this is still challenging. Consider that if this is like a pedestrian 3, he plans to cross the parking lane from right to left. And when at the beginning he's at here, you can see his heading angle is typically 45 degree, and the gazing angle is typically 90 degree because he needs to check the incoming traffic on the left side. But when he's moving to the middle of the road, he may turn his head to the right side by 45 degree with a gaze angle like a 70 to 90 degree to check the traffic from the right side, which means and for the entire trajectory, he only moves forward. So which means there's not a strong correlation between either the head angle or the gaze angle. So yeah, and for example, another example is a number 4, pedestrian number 4. He's pushing a shopping cart. Firstly, we need to know if his shopping cart is empty. It's empty, which means he may, just return the cart to the cart collection area, left or right. But if there's something in the cart, we need to know where is his car because he's mostly heading to his car. So because it's a random event, we don't know where his car is. So it's very challenging to predict his trajectory. And another challenge is we need to understand the intention of the road users. For example, if a mad driver is talking to a driverless car, so it will be pretty interesting. I don't think the car can understand what he's talking about. And some easier like signs, hand signs from the road users, maybe like this figure shows a policeman is directing traffic, and this is someone just use hand to tell you stop. Maybe easier to understand. And but not always. For example, if a pedestrian in the middle of the road crossing to the other side, and then we are waiting, a driverless car is waiting in front of him. The pedestrian keep waving his hand, oh, go, 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 you go first. And the driverless car, because it never got trained to understand the hand sign, so it will stop. And then the pedestrian will keep waving his hand and the car will keep stopping in front of him. It will be kind of interesting and awkward. So in order to make it fully autonomous, firstly, the driverless car should understand all of these hand signs. For example, the cyclist turn left, turn right, and stop. Even this one is confusing because both these two gestures is showing turn right. And for cars, I just Googled these pictures because I never saw in the real case any drivers doing something like this. And it's still confusing to some, even to me, like this one showing he wants to turn right, but his left hand is reaching out. But this is their language to show which side they will be turning to. And this is for stopping. For the first time, when people see this, I don't think even we understand. Like this picture is showing like probably in some other countries, driver sitting on the right hand side. Like this is turn left. I don't understand why this means turn left. And also slow down. I think they are pretty similar. And So this case is pretty common, like in a four-way stop, like 2 or 3 cars happen to stop at the in front of arrive at the like a stop line at the same time. So one of the driver just wave his hand, oh, please go, I will yield first. And the other car driver maybe raise up his hand, oh, okay, thank you, I will go first. But you can imagine there's a driverless car, there's no driver. So everyone will be confusing. And the driverless car, I don't know, depending on what's the state machine in its computer, it either wait for all the other cars pass and then it will go, or wait for several calculatable seconds and then the car will move forward. And also, for example, besides the hand sense, also the car also need to understand the vehicle's light sense. For example, if a front vehicle suddenly suddenly slow down and then turn on his hazard light, probably means the driver want to do a temporary like illegal parking, and then ask his intention should be ask the following cars overtake it and move around it. But firstly, we need to understand. Otherwise, the car may just the driverless car just like wait forever. Yeah, those are some examples of current challenges in the automated valet parking development. And yeah, so we welcome our my colleague Tanto Sugiyaki. So yeah, Tanto will introduce some more details about the motion planning we are using and also the challenges in the motion planning. The mouse is underneath.
Oh.
Yeah.
All right. Okay. Thank you. Yeah,
And there's the laser point.
okay. Hello, everyone. My name is Tanto Sugiyato. I've been working with the World Group on the autonomous drive L2+ system for about 6 years. Prior joining the team, I was working as a power electronic in the motor control for like almost the rest of my entire career since I graduated from school. And today I have a privilege to talk about some aspect about our planner that is in the parking system. We call it a slot planner, which is the job is to figure out how to get from one spot and then to get into the goal point that is leaving the car. Is in this case it's going to be parallel parking. It is a major technology where almost autonomous drive. They have that park assist feature that most people doesn't use it, but something still need to be developed in order for us to be able to sell our product to our customers. And given it is a major, there is a lot of algorithm off the shelf that you can check it out. There's a GitHub link or there's a research paper that discuss about it. But there is issue here. There is nobody tell us which one that is working robustly. And we always have struggled between figure out what is the robustness of the algorithm and what we can fit into the embedded processor that requires a high-speed computation, but you cannot exceeding some certain amount of time limit. Some OEM maybe says 2 seconds, some are can be longer, 20 seconds, but we don't know it is. So I'm just listed the type of algorithm that is I can think of that from the searching. One of them is a geometric planner. It's a very cheap algorithm. Mostly it's a handcrafted type of algorithm, or you can use like a obstacle-free type of motion planning, like a reach share. It's very fast. However, there is a problem is you cannot, since the algorithm is not completely aware about the obstacle around it, so you sometimes have to end up into the coming to the heuristic rule base to figure out how to avoid the obstacle, especially in the corner case scenario. The second approach is to use a search-based type of planner. One of them is A-star, hybrid A-star. Which is pretty good. It's a greedy based. Once the solution is found, then it's guaranteed that it's going to be optimal. However, even the nature of it is a dynamic searching. The compute time can be pretty huge, especially if you don't have a good resolution in grid, or it can be like some corner case where there's obstacle that is being arranged to pipe inside. The third one, that's something that is also happening the later on the research paper, is the nonlinear optimization, where we use sort of like a nonlinear optimization, like what we normally use in MPC, but instead of following the path, the problem is reverse. We need to create the path that is going to bring the point from one point to another point that can safely avoiding the obstacle. And the last one that we also start investigating is the reinforcement learning. So we try to understand, can we train the machine to think instead of what we normally do with the supervised learning, we try to mimicking what is the label data set input versus what is the correct behavior. And it is interesting concept, but still some challenge of it, especially that we have to create an environment, simulated environment, and how to infuse the human behavior into it. Another challenge that is outside the algorithm itself is the trade-off between the compute time and robustness that I mentioned, and the accuracy of the perception. When we say that we want to have a precision like a 20 centimeter, which is about the size of our side mirror, are we sure that our perception system can have that amount of resolution, and that thing can cascade into what we can do in subplanar engineer to provide some safe time. And another thing that is something that is what we see a lot in our test case here is the localization error. We don't have a, not unlike in highway, you can use like a lane detection to evaluate the center line. Our system here, we have to create our own path, and in order to follow that path that we created, we need to have a good, precise localization system that is quite stringent, because we cannot have a localization that of 30 centimeter or 20 centimeter. We have to be almost within less than 10 centimeter accuracy to avoid any plumb into the curve or into another part of the. And another one is the control system itself. Not like in the highway system where we can almost infinite waypoint that we can follow. But in the purposes as the end point where the control need to immediately stop when we reach a certain point. Otherwise, we might bump into another vehicle that is purposes into us. And I bring a toy example here on the most left side here. That is one of the solutions from hybrid star. It is, we do have a gap when the vehicle is parked. We only have a gap about 40 centimeters with the front and the back. And this is a real scenario that is being requested by one of our customers. And this, so I just going to show it here. I hope the video is running. Yeah, it's interesting on how that algorithm can decide on how to make a maneuver back and forth while avoiding the obstacle and finish into the final spot here. It's pretty slick, but if you ask me, does it work in the real application? Maybe not, because our perception system has some limitation. Our localization has some error. So that's something that we have still investigating how to best way. And also on the plot on the right side over there, I'm going to explain a little bit. The one on the left is the one that is fail case. We are not able to get part into the what our intended goal point. The one on the right side is when we do have a successful scenario here. Then I try to understand if I plot all the nodes. This is using the hybrid star application. If I plot all the nodes that I have been visited during the searching, what is the node looks like between the failed and the successful state here? Looking at the picture here, unfortunately, I cannot tell the difference. What make it successful, what is not making it unsuccessful. However, what I notice here, there is an area here that is, as a human being, we are not even supposed to consider it. Like we are supposed to part from this position to get into the goal, but the hybrid A-star, even though it's kind of like a smart algorithm, they still searching some area here that is not even we are not supposed to even consider as a human being. And also the same thing I noticed over here. There's maybe another area that we need to look at it. It's like, can we make our heuristic algorithm that is part of the A-star or hybrid A-star a little bit more smarter? Maybe there's something about machine learning that we can further explore to make this one, because this type of problem here, if we can solve it, definitely we cut our competition apart significantly. So there is still like an open question that we still try to do investigation. And I'm going to bring the talk back to what about the opportunity that we have in our field here. Thank you.
Thanks, Tonto. Well, if any of you like these kind of challenges and you're interested in working in the automotive environment, particularly for Aptiv, we hire lots of folks, right? Both interns and full-time. Once you graduate, we hire a lot of engineers, right? I mean, if you look at that list, right, the vast majority of the people we hire here, at least in Indiana, are engineers. For our internships, we have a minimum GPA. We have internships available at all of those US sites, right? So our internships for this summer were filled last August and September, right? We have recruiters that come. I think you have fall jobs fairs, right? We do a lot of interviews there, but your best chance of really understanding what's available, right, and make sure you don't miss anything, is to go to jobs.aptiv.com, right? You can look in there, everything from our full-time, from manufacturing all the way down to internships, and all the engineering positions are posted there, right? So, I looked just a couple of nights ago, there's 43 openings in Carmel, right? 41 of them were engineers. Okay, so that should hit a pretty good sweet spot with the crowd here tonight. So I think that might be it. Oh yeah, just few pictures. These are our interns from last year at some of their celebrations. Top picture is in our Troy headquarters. The bottom picture is actually it's actually our full staff out in Los Angeles. They're in Agoura Hills. They used to be in Malibu, right, overlooking the what was the name of that TV show? Come on, Malibu, with the lifeguards and things. Anyhow, so anyway, this guy right here, he was an intern in LA last year. He's getting his master's degree this May, and he's going to work for us in Carmel starting middle of May. So his name is Goro Ye. So we're excited to see him. On the next slide, there's interns from our site in Warren, Ohio. These guys were in Carmel last year, and this guy right here, Rohan, I don't think he's here right now. Rohan Mana, right? He's getting his PhD right now here. So he's off in a meeting right now. He was going to try to make it before the end of this discussion, but you can ask Rohan about his experience at Aptiv. So with that, I guess I'd like to open it up to questions.
Yeah, let's first thank the speakers. Any questions?
Oh yeah, Professor, please. Go ahead. Yeah. Hi.
Okay.
Yeah. Why don't you want to go ahead? Yeah.
So you mentioned earlier about how cheap the sensors are, or a lot of the sensors are pretty cheap on the vehicles, and the difference between like L1 and L2 and L3. Does once the vehicle is developed and those algorithms developed, does making the car smart materially increase the cost of the car, or is it just the overhead of doing the research that adds the price to the car?
We're moving from a fixed software cost now to a software services model. Kind of like the phone plan, right? They give you the phone free, you pay a service per month, right? For whatever features you want. They're going to that at all the OEMs, right? I think Tesla kind of started that, and all the others are starting that. If you have capability in sensing and compute on the car, and the OEM releases like a new feature or function, right? They're going to ask you to pay for it, right? So is that what you're asking for?
Yeah, so I guess the follow-up question is that if you have like a safety feature that the car is able to do, but is disabled, that could potentially still like save lives. Is that a good decision to?
That's not the way the OEMs look at it, right? The safety that your luxury car gets, right, should be the same that your low-end car gets, right? There's a basic safety there that you're going to have. Some of these other features, the autonomy features, right? Those are optional, right? So the people that can afford some of the more convenience and safety autonomy features, right? Those are cost adders. But your basic safety you get with any car.
Brent.
Oh,
Yeah.
Okay. So Mr. Kozak, right? Am I pronouncing it right?
Yes.
Sorry. I really appreciate your vision towards the radar sensor, right? So far we are also building like the autonomous racing cars. And those cars can go up to 170 miles an hour. And we are also having a lot of sensors, including LiDAR and radar. But the kind of the dilemma we are facing is that the radar is really hard to detect accurate objects, especially at a very high speed, right? So what I'm thinking is that we're facing this kind of dilemma. So in your opinion, should we go to make the software more smarter to get rid of those noise and to make accurate detection, or we kind of squeeze the hardware to make build better hardware? So basically, either you go from software or go hardware. Which way you would suggest us to go?
You guys have any comments on that?
I think firstly, depends on what kind of radar you use. Some of the corner radars, they are low. The resolution is not as high. But
You mean the frequency, right?
the resolution, I mean, we will say some like false detections.
Yes.
Only because of the resolution. For example, the vertical resolution, it tells like there's something in front, but actually it's no height. Yeah, no height. But there are also some new radars with so-called 4D radar, imaging radar. It has a much better vertical discrimination or the elevation discrimination. Like Tesla is doing for Tesla is inventing some of the radars. But I think if the radar's resolution discrimination accuracy is better, there will be less false signals. Okay.
And I think the problem you're probably dealing with is your racing team, probably got a kit.
We do have a kit.
And the kit came with a long range radar and the other stuff.
We can upgrade the hardware also, right? So
Okay.
basically, should we go to improve the hardware or we improve the Yeah, so currently we are facing the dilemma is that we cannot detect accurate as LiDAR.
Yeah, so the radar, it has a electromagnetic waveform, right? At probably 77 gigahertz. That's probably what the radar is, right?
Yes.
And that waveform, contains range rate or Doppler and angle, right? And they have to kind of unfold all that. Yes. Right. Your Doppler unfolding generally has a limited speed, right? Maximum speed that it can see. Yeah. Right. So I don't know if your problem is the fact that you're going faster than the radar can see like other objects, or if it's just you have so much noise, I mean, these radars weren't necessarily developed for, banked tracks.
Yeah.
Right, at those high speeds.
Yes.
So, yeah, and your angular resolution probably isn't really good, right? So, you may just hit a technical limit, right, to the radar, right? You're using an automotive grade radar likely, right, in an application it wasn't designed for. So I guess I would tell you is to look at the specs, right? If you want to upgrade your radar, right, look at the specs and how they compare to your existing radar, and then compare that to the LiDAR, and try to understand, a radar is very good at range and range rate, right?
Yes.
Velocity, right? Not so good with, it can't give you a dense point cloud,
Yes.
right? So I don't really know what you need. Right?
Yeah, so right now we are building like a fusion algorithm. We use both LiDAR and radar, and then we use a cover filter to kind of fuse all this information to check it. And then we are also facing a problem. We don't know like the uncertainty of my radar. We have so much noise, and we cannot know like the magnitude of this noise, and we couldn't build that covariance matrix for the cover filter. That's we are a little bit awkward here.
I think this is related to the posing protection.
Yes.
I think I'm not sure about the package you get. Do you have a tracker?
Yes, so that
Okay, so probably maybe something wrong with the tracker calibration. The way this is before.
Frank, I would just suggest you to buy one of those. That's easier.
$20.
While the students are asking questions, should I pass those around or?
Yeah. Or they can come up after too. If they want. Next question? You have?
Yeah, I have two questions. First one is I wonder what your insistence about the false negatives phenomenon. That means that some detector or some sensing technology can detect all of that. However, actually there is no any of that. So in this case, what is your the distinction of priority in your systems? That is my first question. And the second question is, I think automated operations is very important if AV is more popular. So in that case, is there any big logging problems like seeking some available answers? So I think it is very, very important because we don't know any available answers. I think particularly will be lower. It makes more emissions and other fear. So is there any concern about the vehicle logging systems in your platform?
Now, for the first question, what's the first question?
Yeah, first question is on the sensor technology can be.
So the false positives.
Yeah.
Yeah, if you only have one tap cipher like a radar, if there's a consistent false negative, like there's something consistently cannot see that, there's nothing we can do. But if you intermittently cannot see that, then we can use some like missing data like a processing and to fulfill the gap. If in the like if it's 10-second tracking, in the first 5 seconds and the second 6 to second 10, we can consistently detect that. But at the second 5, we miss that. Then we can do some temporal fixing to see, oh, this is a fault connecting. If you consistently cannot see that, and then there's nothing we can do. But if you have multiple types of sensors, like if you have cameras can see that, radar cannot see that. So that in different kind of sensors is separated to each other. Then you need to do a fusion to decide, to make decisions. And the second question I think is related to the parking space. If you cannot find it in advance, like in the pretty crowded parking lot, you can only pass that to see, oh, here is a parking spot. I think one of the benefits of radar, advantage of radar is like the radar can see something being blocked by another thing. Like if there's a car and then there's another car behind that or in front of that, radar can see the being blocked the car through the ground reflector, which means the radar has a better chance of seeing front like the green space, parking space.
Part of the question though was, what if there is no open spots and this car is just, it's hovering around, right? Going up and down, creating emissions, right? Running out of battery. Lots of things, right? That's certainly a problem, right? In our system right now, if it goes, and it can't find spots that, it normally parks in, right? It raises its hand and it says, hey, I'm coming back, right? Because I couldn't find a spot, right? Now you can use the infrastructure to tell you where the open spots are too, right? You pull into a park garage, it says there's 18 spots available, it has a map, it downloads the spots, right? And you just pick one and you go to it, right? So that's easy. Another thing this automated parking does is, automated charging too, right? Where you can schedule a time, right, for it to pull up to maybe a wireless charging pad, right? And charges your car while you're at work, right? And it's waiting for you when you're ready to leave. So a lot of these systems, may not work like autonomously without a little help from the infrastructure. Where are the charging pads? Perhaps there's fiducials or barcodes, right, that tell you exactly what that spot is and if you're allowed to park there, is it handicapped or not, things like this. So there's still, obviously it's not in high volume production yet. It's still under development.
So my question is, do you have any plan to collaborate with some the government or some parking system operators? So that's my question, because I think it's better to combine some information about the parking infrastructure or some government information. I think it will be better with your system.
Yeah, at least in the US, there is no single entity to work with, right? All the park houses are owned by different commercial organizations, right? You can't go to the federal government and say, hey, we need to install this in every park garage, right? Because there's state, there's local, there's too many different entities. That's why V2X hasn't taken off, right? There's 160,000 intersections in the signalized intersections in the US, right? You would have thought someone would have been able to just wave their hand and have V2X come to pass. Well, it doesn't work like that here in the US. So hold on a second.
Probably someone else.
We have had a lot of questions. I think we can go faster with.
Probably.
Well, there's several others. So
So I'm curious about how powerful your onboard computer is, because I know you got lots of constraints, like the heat, something. So that will also affect the algorithm development. So
yeah, I don't. Can you quote the gigaflops or anything else like that?
Yeah, I don't have the number on top of our development system is similar to the PC system. It is quite capable. You can run multiple modules running together. Some of them benchmark it. It's really reliable. That's at least for our development system. And then we are ready to talk about to implement the system. We want to monitor about the system, the capacity of the system, make sure that it's working. That is not part of our future because we have to focus more on the development.
Yeah, we use PC. If PC has CPU and GPU, we just use that. Yeah.
But, yeah, but we do profile it, right, and understand whether it'll fit in the embedded platform. You know, one thing that, you know, you might not be aware of is, right, we're really, our customers don't allow us to violate more than 80% of the microprocessors resources, right? We need to have headroom there because they know there's going to be ongoing changes, right? So from a memory and you know, processing throughput standpoint, most of our algorithms run on what, like a 25 millisecond boot time, 25 or 50 millisecond.
Yeah, some safety critical algorithms across the ecosystem stability and people you know like pretty fast and but some algorithm like a slot planner that you can see for a while really again rather than one of the systems. So we prioritize this algorithm that safety critical, we want to run it as fast as possible, but one that you can put it in the order.
Like collision avoidance is probably 100 milliseconds. Depending on where you need to compare, like compare to a human driver. Human driver make decision, the time is about 50 to 500 milliseconds. If autonomous vehicle is faster than that, it's okay. Let's see. Thank you.
David, or David, go first.
The fascinating about mentioned radar like with cameras on your vehicle.
Well, we personally haven't dealt with LiDARs yet.
Okay, so basically radar.
Mm.
So here's a question about when you're basically in this situation, see two overlaps with maybe high relatives like coming towards you or coming below, and one of the vehicles also like the other. You mentioned you use radar, or you believe that radar can see through that operation around reflecting or something like that. If you have two conflicted, like camera tells you there are only one vehicle, or maybe 1.5 or something like that, radar tells you there are two, which type of source you believe?
It depends on which like if perception, if this question to perception people, it's a good question, and it's it could be a problem because they need to provide bounding box to us. One bounding box and two bounding boxes, they are different. But from a motion planning point of view, it doesn't matter. It's two obstacles or just one non-obstacle. From collision avoidance point of view, it doesn't matter. So they basically treat it like one obstacle. That's okay now. Even if it's two obstacles, they are the same in the collision avoidance point of view.
And by the time you get close enough to it, they separate.
Yeah.
You know what I mean? And by the time you need the control to one or the other, right, then you can see them.
From my understanding, it's just basically ignore that difference.
Yeah, it doesn't matter at this stage, right?
Sometimes separate them.
And I do think the perception can perception team can separate these two because when two cars are driving, their wheels are also rotating. If there are like for example, the first car has 4 wheels and the second car has 4 wheels and only 8 wheels if detected, probably 2 cars. But if some other cars like the 18 wheelers, it's another story.
Or maybe the difference of their speed.
Maybe speed are the same, but numbers of wheels, tires,
I see.
may tell something.
And another question is about motion planning. Algorithm mentioned so SDN, where you're basically predicting the interactions with surrounding vehicles and pedestrians and things like that. And then mentioned this A-star searching algorithm along with reinforcement, right? So in total, 3 types of algorithms are lots of computing power. So I wonder what's the expected delay in the system for your sort of handle this kind of complex work, something like that. You have in total 3 types of this algorithm.
Yeah, I think that's interesting to observe here. One, you need to separate the like what type of planner that is currently used within the context to the requirement of the vehicle. Is it's good that we might have other people. Algorithm that is high compute, but not necessarily all of them need to be run all together. That will suck up all the CPU power. For example, when we are on a using mode, we can run our local then do some heavy computation. People on what I'm doing, do perform certain action to avoid a mistake. That's fine. When we run the local implementation, unnecessarily we have to run a software at the same time. We can keep it. Thank you.
So, yeah. It's a good question. Have you guys considered cooperative communication between networks of autonomous vehicles? Is that kind of on your horizon, or is that like a little too far down the road?
It sounds like, I mean, it sounds great, right? The problem is, there's 100 million vehicles on the road today that don't have, they're not cooperative. So, your autonomous system has to work without it, right? Anyway, so, from a research and a theoretical standpoint, it's great, right? You all know what each other are doing. It's all coordinated. There will never ever be an accident, right? But unless you actually retrofit, right? The government regulates and requires retrofitting the technology into like the existing fleet that's driving around. It's really only a paper study, right?
Well, hypothetically, like in the future, even if only half of the cars are autonomous capable, would that hypothetically still improve safety if there's like not necessarily, they're coordinated movements, but that maybe communicating.
Yeah, I've heard that the tipping point is like 70%. Right, I don't know if that's still legit, but years ago when we were studying DSRC based V2V, right, the tipping point was 70%. So that was another point I was trying to make, but I mean, we had the first DSRC based V2V out on the Cadillacs a few years ago, right? The CT6s, right? They sold like 5,000 in the US, right? So there's 5,000 cars running around that can talk to each other, but they can't talk to anybody else, right? So it doesn't do a whole lot of good, right? So
They also privacy concerns. If some other what they are doing, if they share something,
it's all anonymous though. Right.
Well, you can, I'm sure there's encryption and what you can do between passing information.
Yeah.
The widespread adoption, I guess, is the major bottleneck.
That's been the biggest thing, right? I mean, all of the proponents for V2X, right? They want the government to step in and regulate it, right? Not just regulate it for new cars, right? But make it retroactive for the existing fleet too. And once you have that, I mean, you come up that curve real quick, right? And then,
well, I assume that if you have cars that have these capabilities built in, you can potentially do software updates on a car. If you have the sensor and the brain in there, if it's just a matter of can that.
but what's the business case for the OEM? Why do they want to put another $20 of cost in this car that they may or may never use, or may never monetize with some subscription, right? When they could put $20 in their pocket instead, right?
Sure. So it would come from a regulatory standpoint.
Yeah, it has to, right? Big brother government. So the other thing is, you're still going to have manually driven, we're getting into a mode where there's manually driven and automated, right? So in that mixed environment, right, it's the humans that are the wild card, right? You never know what they're going to do. Sure. Right.
Thank you. Next question.
I have a quick question. When you do the autonomous parking, you do tell whether you can parking before you start the parking process?
It's depending on if the parking space planning module can tell us the accurate size of the parking spot. It is the size is enough for a car to put in, and then we will see if there's something like if this is by a fire line, like we cannot park, but some rules. If all of these are satisfied, then we can make decision before we reach to the spot. Okay.
So generally, we don't have a detailed map of the parking area. Right, so this home zone parking that he showed the demo, right? It's a memory or trained parking, right? You you get in the car, you hit train, and then you drive the car to where you want it to park, right? And then it kind of memorizes that. It creates a self map, right? Similarly, if it needs to come back in a different direction, right? You train it for your pickup or your summon, right? And again, we're creating a map, right, based on our radar point clouds and our camera features that we see, stop signs and things like this, right? And then, the next time we tell the car to go park itself, it's just like a dog, right? It follows a breadcrumb trail and goes to where it's supposed to park. Now, we still have to tell whether there's someone else in the spot or if the spot next to it's open or something like that, right? But right now, our L4 parking, right? It's not sophisticated enough because the maps aren't high fidelity, right? If you had a map from the infrastructure and it told you how many spots there were, how many were handicapped, and how many were electric vehicle charging and things, right? I mean, you could tell one-way streets up a ramp or one-way travel, right? Right now, we don't know that, right? It doesn't know the rules.
If we know, we only need to vary about the size. It is enough for a car to move in.
Probably we'll take one more question and then we can have some offline discussion to the speakers. Anyone want to have some last minute question? Or probably I have one question and that's my question. So Chen, you talk about that automated parking in the parking space. I'm just curious about, because you talk about, the gaze or the head position of those pedestrians. In this case, you are using a camera, right? Because there's no way using a radar to detect all those.
Right.
And how do you think the major challenge of that is it the prediction of this pedestrians' behavior or the detection of their behaviors?
I would say both. Both are important. Since I'm working on motion planning, so prediction of the trajectory of moving obstacles is very important. And I would like to have the next 3 or 6 seconds information, the waypoints or the probability, trajectory probability. And behavior is also important. Like we need to understand what the road user's intention. If he wants to move first, if he's in a hurry, but we don't get his point, there may be some some potential collision, crash or something. So I would say from the motion planning point of view, both are important.
Okay. Thank you. Yeah, let's really thank the speakers one more time. For visiting us and do check out their website, and they're in Carmel, which is very close to us, very big building as well. So feel free to have some offline discussion with speakers. And thank you guys for coming.
Thank you.
Thank you. Thank you.
Best of luck, guys. Hey, if you could make sure all of our samples are.
Yeah, right here. Yeah, I collect all.
Thank you.
5 of them, right? So we have 5. Something like that. Right here. I think I would say the most engaging talk for a long while. Yeah, most engaging, most interactive, with the most questions.
Well, good, and they all braved. Hey, stay dry on the way home.
Order